Hello, everyone. Thank you for coming. I'm Wesley Fussner. I'm a logician at CNRS in the Université Côte d'Azur, France. And I would like to talk to you a little bit today about some recent work that I've done jointly with Gavin St. John of the University of Cagliari at the intersection of quantum logic and substructural logics. So this work is anchored in the orthomodular lattice approach to Birkhoff-von Neumann style quantum logic. So we're very much anchored in some kind of algebraic techniques for studying quantum reasoning. I would like to discuss this just as a roadmap today because the paper is available and I hope many of you read it. So I would like to discuss this roadmap roughly in two parts. First, I would like to give you some background regarding things like algebraic logic generally, just a snapshot of what this is, what this means for the study. Some things like basic quantum logic in this Birkhoff-von Neumann framework studied via orthomodular lattices, and in particular, some problems related to the orthomodular lattice approach. I would also like to discuss some new connections that have recently become prominent between this theory and the theory of substructural logics, which is a big area in non-classical logic, subsuming many applied logics. So our contributions involve the theory of what we will call residuated ortholattices, which are generalizations of orthomodular lattices that I will sketch for you a little bit later on. And I'll discuss some advantages of the residuated ortholattice approach, potentially over the orthomodular lattice approach. And I'll show that some of this stuff is warranted by a Kolmogorov style negative translation of orthomodular lattices into residuated ortholattices. So to begin with a little bit of context, all of this is sort of anchored in the groundbreaking work of Birkhoff and von Neumann in 1936, celebrated paper regarding the logical foundations of quantum mechanics. This idea, I think, was very much animated from this algebraic tradition where you might think about propositions as having truth values in Boolean algebras in classical logic. The idea behind quantum logic in this Birkhoff-von Neumann framework, I think, is that truth values should not be taken to be values in a Boolean algebra, but rather the closed subspaces of a Hilbert space. This is related to the Hilbert space formulation of quantum mechanics. And somehow the closed subspaces should correspond to experimental propositions, say, things that somehow can be tested, at least in principle. All of this is sort of abstracted away from Hilbert spaces, which are quite difficult to study. And you might think instead of orthomodular lattices, which are something that provides something of an abstract characterization of the lattice of closed subspaces of a Hilbert space. And here the points of orthomodular lattices will replace the points in a Boolean algebra on a logical level. This kind of general way of thinking about quantum logic has seen some applications. It's been a very popular formalism in quantum mechanics, although today it's perhaps old-fashioned. It's seen some applications, for example, in quantum computation, where you see in the work of Ying, for example, there's some work on quantum finite automata, stuff like the acceptance in regular languages, Kleene theorems, sort of classical results from theoretical computer science along those lines, but important to the quantum setting. Now, all of this for us comes from the direction of algebraic logic. Algebraic logic sort of takes the idea of taking truth values in Boolean algebras, using this as a semantic environment and generalizing it to having truth values in other kinds of logical algebras. This is a very general sort of approach to thinking about logic, where you might think about having an abstract consequence relation denoted like this turnstile, where you might read an expression like this thing that I'm pointing to as something like phi is a consequence of gamma in the logic L. Now, we interpret this abstract consequence relation turnstile in an equational consequence relation in algebraic logic. And this is an extremely powerful technique because equation consequence relations are very transparent. This kind of reduces the notion of abstract consequence to the notion of reasoning with equations that you might think of from elementary school mathematics, where you take variables, you substitute expressions for variables, and you turn around directions of equations, etc. Here, this is kind of affected by taking the equational consequence relation, which is denoted by the following, say, if I have some set of equations theta, and I take some particular equation epsilon equal delta being a consequence of theta, this means that in any algebraic structure in a given class of algebras K, if every equation in theta holds in this algebra A, then epsilon equals delta does too. This is what it means for epsilon equals delta to be an equational consequence of theta relative to the class K of algebras. And you can always extract from this some class of, if you start with some class of pointed algebraic structures, say K, you can always abstract a logical system from this, so-called the assertional logic of the class, simply by defining consequence in exactly the way you might expect by doing this. I define this abstract consequence relation turnstile K just by transforming the formulas of the logical system into equations and thinking about algebras that satisfy the corresponding equations. And in this kind of framework, logics, at least the logics we'll be interested in today, correspond to varieties of algebras exactly. Varieties are classes of algebras that are defined by equations or equivalently closed by undertaking homomorphic images, subalgebras, and direct products. So a particularly important class of algebraic structures which we'll be concerned with today are the so-called bounded involutive lattices. A lattice, for those unfamiliar, a lattice is simply a poset that has finite infima and finite suprema. And these are denoted by some corresponding algebraic operations, which I will call meet and join respectively. So I take a lattice, if I'm working in involutive lattices, I start with a lattice with a greatest element 1 and a least element 0. And I add to this a unary operation that satisfies some kind of conditions you might expect a negation to satisfy. For example, the law of double negation and the De Morgan laws. Now, we're not just concerned with involutive lattices here. We'll be concerned with involutive lattices where the negation is somehow a complement. So these are called ortholattices or OLs. And you can define complements equationally. So ortholattices are a variety, as I mentioned before. Boolean algebras are perhaps the most commonly known variety of ortholattices. These are precisely the ones that are distributive or meet distributes over join or vice versa. But there are many non-distributive ortholattices as well. Now, if you think about the closed subspaces of a Hilbert space, these certainly form an ortholattice, but they're not merely an ortholattice. They have some additional properties. And the most prominent such property is this orthomodularity law, which I've displayed on the slide here. Here in a closed subspace of a Hilbert space, I think of this negation as being something like the orthogonal complement of a subspace. And the orthomodular law has some kind of geometric meaning for the closed subspaces of a Hilbert space. And this has been an extremely important and influential notion in the foundations of quantum mechanics, or the logical foundations of quantum mechanics at any rate. However, it introduces a lot of complications from the algebraic perspective. If you're an algebraic logician, your ability to progress with the corresponding logical theory hinges really on your ability to understand the algebras that you're dealing with. And if you add this orthomodular law to the base theory of ortholattices, then there are many different complications that arise. For example, ortholattices behave well under completions. Completions is some construct for introducing infinitary infima and suprema in a lattice. Ortholattices behave very well under such things, but orthomodular lattices do not. This also induces some kind of complications for decision problems related to the algebras and the corresponding logics, to relational semantics. This creates some additional problems for relational semantics in the modal logic or intuitionistic style that are not present without orthomodularity. And it also creates some problems in generating nicely behaved proof systems, Gensen style sequence calculi, things like this. All these problems are essentially due to somehow the shape of the orthomodular law. And by that, I mean the order properties of the different connectives and the way that these connectives are composed with one another. The orthomodular law simply has a very undesirable shape with respect to these general theories. And this is a well-known problem that's studied in topics like the theory of canonicity in modal logic, for example. Substructural logic, switching gear a little bit here. This is a very large and prominent class of non-classical logics that have many applications. Perhaps most prominently, they have applications in computational resource management. You may have heard, for example, of linear logic or bunched implication logics, which are examples of substructural logics. And there's recently been quite a lot of work at the intersection of orthomodular lattices and substructural logics, and commensurately also at the intersection of quantum logic and substructural logics. You see this, for example, in the work of Chida and Langer, and more recently the work of Fazio, Letta, and Pauli. All this stuff is sort of linked, if you consider algebraic models, by this condition that's called residuation. Here, in all of these logics, you have some notion like that shall denote by dot. This is some kind of strong conjunction, an additional kind of conjunctive connective in the logics. And this dot has this kind of residuation property where there's another operation that you may toggle to the other side of inequalities, as in the displayed equivalence. Here, as I said, you think of dot as a kind of conjunction, and you think of this division operation on the other side as being kind of an implication. In orthomodular lattices, the well-known Sasaki product operation is the kind of strong conjunction we might want to consider, the quantum conjunction. And it's right residuated in this sense, in exactly the sense I've given above. And its residual is the well-known Sasaki hook operation, which supports this interpretation of the Sasaki hook operation as being an implication for quantum logic. For us, this will not be the case, however. We will not take the Sasaki hook as being the corresponding implication. Instead, we will zoom out and look at structures which are a little bit more general, but still motivated somehow by these connections to substructural logics. In any bounded involutive lattice, I can define the Sasaki product and Sasaki hook, just as I would in OMLs. And I will focus on the Sasaki product, although everything I'm doing could have been done with Sasaki hook instead. The key definition of the structures we're interested in are these so-called residuated ortholattices, which I may call ROLs. These are expansions of bounded involutive lattices in this signature by an additional binary operation, which I'll call under, that satisfies this residuation condition with respect to the Sasaki product. Now, as I mentioned, in general, this division-like operation or implication-like operation does not coincide with the Sasaki hook. Residuated ortholattices do not generally satisfy the orthomodular law either. And in fact, a residuated ortholattice is an orthomodular lattice exactly when the division operation is the Sasaki hook. So sort of in this case, you reduce to this well-known orthomodular lattice case. Residuated ortholattices come with some kind of benefits of working with them that are not present if you think about OMLs themselves. First of all, residuation is a very nicely behaved property with respect to many of the things I mentioned earlier, such as the completions of lattices, such as proof theory. Residuation really has its origins to a large extent in the development of nice proof theories for logics, etc. Stuff like this. I think residuation is a very well-suited candidate for reasoning in this kind of setting. On the other hand, orthomodularity is quite problematic for many of these things. And if we work in the setting of residuated ortholattices, we've eliminated the orthomodular law. We no longer have to deal with this kind of undesirable order properties of this governing equation. An additional benefit of residuated ortholattices is that by studying them, we further get some insight into connections between quantum logic in the OML sense and substructural logics to kind of deepen the emerging trends in that direction, the emerging connections, which may lead to some nice discoveries. We do, however, retain many of the nice logical properties of orthomodular lattices. For example, the residuated ortholattices are still the algebraic semantics of well-behaved logic, which one could write down via this assertional process that I described earlier. And we also get some insight into orthomodular lattices themselves from this viewpoint, because for many purposes, as I hope to convince you, we're studying residuated ortholattices is actually a good way at getting at what happens in orthomodular lattices without having to worry about the difficulties of orthomodularity. What underwrites that is this Kolmogorov style translation that I mentioned earlier. So this is a little bit technical, but this feeds into the notion of negative translations, as you may have heard of from classical and intuitionistic logic. The classical negative translations, such as the Kolmogorov translation or the Glavenko translation, what they do is give a way of interpreting classical logic as a fragment of intuitionistic logic. Now, this works in more or less exactly the same way, toggling between orthomodular lattices and residuated ortholattices, or equivalently their corresponding logics. So in detail, if I take T to be some term in the language we've defined, then I can introduce a second kind of negation that's not the primitive ortholattice negation, but is instead this one defined by the implication or division connective. And then I can think about double negations with respect to this term. I'll denote that by barring the top. The translation that I would like to point you to is this capital T function, and this is defined inductively on the terms as follows. The constants 0 and 1 are fixed by the translation, and every variable in the language that I give you will be sent to its double negation. The ortholattice negation, neg like so, for any term, will be sent to the second negation that I've introduced under the translation. And all of the other operations like meet, join, and implication will be fixed under the translation. And in a fairly straightforward way, I extend this, as you might expect, to sets of equations as well. And again, all this stuff can be toggled to the logical end where I think about formulas instead of equations via the correspondence I've described. Another key definition is if I take subvarieties of residuated ortholattices, which remember correspond to logics that we're interested in. If I take subvarieties, say W and V, I'll say that the subvariety V is translatable into the subvariety W if for any set of equations E together with a particular single equation S is equal to T, we have that E has as an equational consequence in V, S is equal to T, if and only if the translation of the equations in E has the translation of S equal to the translation of T as a consequence in W. So it's simply the notion of translating V into the variety W. And if you work with this main result, as we've proven in the paper, you can obtain the following translation theorem. So if we denote by ROL the variety of ROLs and OML the subvariety of OMLs, we get the following. If I take V to be any variety that's OML plus some additional set of equations, so some extension of the logic of OMLs, and I let W to be ROL plus the translation of these equations, and I take any subvariety between V and W, then V is translatable into U. And in particular, something that falls out of this technical result is that the variety of orthomodular lattices is translatable into the variety of residuated ortholattices. And therefore, this kind of orthomodular lattice approach to quantum logic, this version of quantum logic is translated into the logic of residuated ortholattices as well. This has some nice consequences. For example, there's the following result about decidability, which I think supports the general project of considering residuated ortholattices for an environment of reasoning about OMLs. Stated specifically, it says that if we take W and V to be varieties of residuated ortholattices, if V is translatable into W, then deciding equations in V is no harder than deciding equations in W. In particular, if the equational theory of W is decidable, then the same holds for the equational theory of V. And the equational theory's decidability there corresponds to the decidability of logics if we toggle back to the logical side of the equivalence. And as a consequence of this, we get the OMLs, so Birkhoff on quantum logic, you may think about it as, OMLs have a decidable equational theory if any variety of residuated ortholattices that contain it has a decidable equational theory. So this supports some kind of notion of flexibility where we can select an appropriately tailored variety of residuated ortholattices and work there. So to sum up, we've introduced this notion of a residuated ortholattice as sort of an intuitionistic environment for studying orthomodular lattices. And this provides sort of a more flexible environment for studying orthomodular lattices in the sense that it gets away from some of the negative algebraic properties that we might have there. And it also deepens some connections to substructural logics. This is part of a multinational ongoing project between researchers here in Nice, some researchers with my co-author in Cagliari, and also some co-authors in Barcelona. And the overall aims of this project as we continue forward are to study orthomodular lattices in quantum logic from this perspective, seeing what we can do in orthomodular lattices, or rather seeing what we can do in residuated ortholattices that we could not do in orthomodular lattices, and import the results down. Hopefully we'll address some old open questions in orthomodular lattices, perhaps their decidability, perhaps questions related to completions, etc. And we also generally would like to import techniques from substructural logic to the orthomodular lattice setting into steady quantum logics. And this also, going the other way, supports existing strands of work in substructural logics, and in particular the theory of idempotent substructural logics. So with that, I will thank you for your interest in this work and your interest in this talk. So thanks for sticking around. I would like to just give you a brief summary of some interesting references related to the topics I have discussed. And with that, thanks one more time for coming to this talk and for your interest in this paper.